So today's class will discuss how to actually calculate buoyant force acting on an object. Okay. Let's begin with a non-accelerated fluid itself. When an object is surrounded by fluids, as we know, the fluid will exert force on the object by means of pressure. Now consider this football in the second situation, which is partially immersed in water. Outside water, there is air. Air is at uniform pressure. Okay, for the size of a football, the pressure in air doesn't vary significantly. So the upper part of the football, which is outside water, is under uniform pressure. So the forces acting on that part of the football surface will be uniform in magnitude. But inside water, as you go deeper, pressure increases and it increases significantly. Therefore, the force acting at each point of the football surface inside, which is inside water, will be varying significantly. It will be like this. Okay. And in this case, there is perfect symmetry. Okay, you can draw a vertical line like this. It's the line of symmetry. Then the resultant of all those orange vectors will be in the downward direction because they are distributed symmetrically and they are of same magnitude. The resultant of all the orange vectors will be in the downward direction. And these red vectors, if you see, they are also symmetrically arranged. Okay, about that line of symmetry. At a given horizontal level, the pressure is same. Okay, this is a non-accelerated fluid, non-accelerated liquid. So at a given horizontal level, the pressure is same. Therefore, forces acting at every horizontal level are the same in magnitude. And you can tell that their x components are going to cancel, y components will get added up. So these red vectors, their resultant will be in the upward direction. That also from symmetry itself, we can say. Suppose you find, or okay, you no need to find or anything. So these forces are arising due to pressure distribution around the object. The resultant of these two is what you call buoyant force. Okay. We now need a method to calculate this. Fine. Let's begin with a simple case. Try this, all of you. Suppose there is a, okay, let's take a cube to begin with. Solid cube. It is fully immersed in the liquid, as you can see. Okay. Cube side is A. Density of the liquid is rho. Okay. Assume the cube is held there. Somehow we are holding it. Let's say there, you can imagine some extra force if you want. It is holding the cube there, not allowing it to sink, not allowing it to rise. Okay. Now you can imagine the pressure distribution around it. The upper surface of the cube is parallel to upper surface of the liquid. And now the upper surface is under uniform pressure. Why? Because all points are at the same depth. But that pressure will be less because the depth is less there. Okay. Then on the lateral walls of the cube, as you go down, the pressure increases. Therefore, the force vectors have to be increasing in length, increasing in magnitude. Okay, these forces will act on the sides, the lateral walls. Of course, there will be forces acting from front and behind also. Those we cannot show in this 2D diagram. And on the bottom surface, the entire bottom surface is at the same depth from the free surface of the liquid. So the entire bottom surface will be under uniform pressure, but that pressure will be higher than the pressure on the upper surface. So this is the force distribution. Now, what gave rise to these forces? Pressure distribution gives rise to this force distribution. Okay. Now you know the dimensions of the cube. You know how to express pressure in a liquid. Okay, this is non-accelerated. So use that idea. P is P naught plus rho g into y, where y is the depth. Okay. use that idea and calculate these forces. The force acting down on the upper surface, let's call it F1. The force acting up on the lower surface, let's call it F2. I want you to write proper expressions for the forces F1 and F2. Okay, do this all of you. I'll give you 2 minutes. And yeah, you will have to make some assumptions, obviously. Assume this upper surface is at some height, okay, some depth, x, okay, some unknown value. Based on that, you all write. Listen, the force F1 is the force acting on the upper surface of the cube. The entire upper surface is under uniform pressure and it's a flat surface. If pressure is uniform and surface is flat, expressing force is very easy, pressure multiplied with area. We had discussed this in the second lecture of this chapter. Okay. Now, what is the pressure on the upper surface? The upper surface of the cube is at a depth x from the free surface of the liquid. Okay. The pressure here is atmospheric pressure. The liquid is open to atmosphere. Then the pressure here will be P naught plus rho gx. Okay. So pressure P naught plus rho gx. X is a fixed value, okay, for the upper surface. Multiplied with area of the upper surface is a square. That's the force F1 which will be pressing it down. Okay. Next, the force F2 acting on the lower surface of the cube. Aishwarya, can you tell how much F2 will be?
So P naught plus rho g x plus a into a square.
P naught plus rho g x plus a all multiplied with a square. Correct. Because the pressure at that depth will be P naught plus rho g into x plus a. Now, some of you may be asking, sir, above this point, okay, which point? Above the bottom of the cube, water is not there, liquid is not there, some other material is there. How are we saying this is the pressure? I told you, no, that materials effect is not shown here. Why? We are holding that object, the cube there. We are not allowing it to press down or go up. Okay, so materials effect will not be shown here. How will pressure get created there? Basically, the surrounding water itself creates the pressure. Like at this point, if you take the pressure is P naught plus rho g into x plus a, then the pressure here, 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 at all points at the same horizontal level will be the same. So the entire base of the cube will be at a pressure of P naught plus rho g x plus a. Multiply that with area a square, you will get the force acting on it. Okay. Why are we doing all this? To finally calculate the buoyant force. Okay, we want an expression for buoyant force now. Oh, fine. There are other forces also acting on this cube. Cube has 6 faces, no? On upper face and lower face, we have calculated the forces. There are forces acting on the lateral faces also. Uh, can any of you tell me, do we need to calculate those forces to find out the net force? Will the forces acting on the sides contribute to net force? They will not. Okay, because there is no horizontal pressure variation in this case. How much ever is the force due to these vectors, how much ever is the resultant of these vectors, same will be the resultant of these vectors as well. So force from left side cancels force from right side. Force from the front cancels force from behind. Okay, these are all part of buoyant force only, but they don't matter now. Had there been horizontal pressure variation, force from the right may not have been equal to force from the left. Then you will have to calculate that force also, that difference also. Okay. So effectively now, the total buoyant force acting on the cube. Now we know F2 is stronger than F1. So the total buoyant force now is F2 minus F1. And if you subtract these, what will happen? P naught plus rho gx into a square will get cancelled. You will be left with rho g a into a square. A into a square is a cube. Rho is the density of what? Liquid, not the object. Rho is the liquid's density. A cube is the object's volume. Now, this is interesting. So basically what you get is density of liquid multiplied with volume of object multiplied with g. Density into volume gives you mass. Okay. But density of one object and mass of another object, you should not multiply. Now this object is taking some space in the liquid. The volume of this object is what we call as volume of liquid displaced. Correct only, no? That much volume of the liquid is being displaced by this object. So volume of object is nothing but volume of liquid displaced by the object. Okay. Density into volume gives you mass. So density of liquid into volume of liquid displaced gives you mass of liquid displaced. Multiply that with g. Mass multiplied with acceleration due to gravity gives you weight of the liquid displaced. This is what Archimedes discovered. The buoyant force acting on an object is equal to weight of the liquid displaced by the object. Okay, and it acts in the upward direction as Archimedes stated the principle. He used the word upthrust. Okay, upthrust means force is in the upward direction, and it makes sense why it is in the upward direction. Pressure increases as you go down. So forces from below will be stronger than forces from above. Buoyant force will be in the upward direction. Okay, so this is the basic case of buoyant force acting on an object, and we proved that buoyant force is equal to weight of the liquid displaced. Now in this case, the object was a cube. So it was easy to prove. What if the object was something else of some other shape? Will it still be equal to weight of the liquid displaced? Let us see. And in this proof itself, you'll understand how to calculate buoyant force generally. Okay. So consider a random object like this. Some randomly shaped object. Let's say it is immersed. We are considering cases where it is fully immersed. I'll also explain cases where it is partially immersed. Okay. Now on this object also, there will be forces exerted by the surrounding liquid due to pressure. Pressure at the top will be less, so force will be weak. But as you go down, pressure increases, forces become stronger. As you go further down, the forces become further stronger. At the bottommost point, the force will be the strongest. Now in this case, it's very difficult to express the force. Why? Because the surface is not flat, pressure is not uniform, and surface is not flat, so you can't simply multiply pressure with area. It's very difficult to express the force. So how do we prove that this will be the resultant of all these vectors will be equal to weight of the liquid displaced? How we do that is by imagining that space was filled with the liquid itself. Okay. Now the container is non-accelerated, means the liquid is also non-accelerated. So what I'm going to do is I'm just going to mark a boundary here. Along the surface of the object immersed, visualize a boundary. This is an imaginary boundary. Nothing is actually present inside. Now remove this object. Okay. So basically what we are visualizing it as is the space occupied by the object being occupied by the liquid itself. Imagine it like that. Fine. Now on that imaginary boundary, the same forces will be acting, which act in this case. Do you all agree with this or not? Will the force distribution be the same or not? In both cases, we are considering static liquid only. Will the pressure distribution and force distribution be same or not?
Yes, sir.
It will be the same. That means the resultant of these force vectors should be same as the resultant of these force vectors. If the forces are same, their resultants have to be same. Okay. Now in the right side case, where the space is filled by the liquid itself, liquid will be in equilibrium. No, it's a non-accelerated liquid, non-accelerated container. Inside that, the liquid is static. So this part of the liquid is in equilibrium. The object may or may not be in equilibrium. If you put a stone in water, you know the stone sinks. Okay. If you put a balloon in water, you know the balloon rises up. So when you immerse some other material in water or liquid, it may stay there, it may sink, it may rise. We can't say. But if that space is filled with the water itself or the same liquid, why will that liquid sink or float or do anything? It will stay there only, it will be in equilibrium. What does that mean? The forces surrounding this boundary are keeping it in equilibrium. Now, on that part of the liquid, weight will also be acting. Now, one of you tell me from what we studied in system of particles, where do we indicate weight of a system to be acting for small systems?
At center of mass, sir.
Center of gravity, which is same as center of mass, correct. Let's say for that part of the liquid, the center of mass is here. Then its weight will be acting like this. How do you express weight? Density of liquid into volume multiplied with g. Okay, mg. That is one force acting on the liquid, that part of the liquid. What other forces are acting? The pressure distribution is creating these additional red vectors. But that part of the liquid is in equilibrium. What does that mean? The weight of that part of the liquid is balanced by the resultant of those red vectors. Otherwise, how will the liquid be in equilibrium? That's the only explanation we can give. So all these red vectors are creating an effect of this much. This is what we call buoyant force, right? Force arising due to pressure distribution. And buoyant force here is keeping this part of the liquid in equilibrium. So it is equal to density of liquid into volume into g. That is nothing but the weight of the liquid present here. Weight of liquid inside the boundary. Okay. Now instead of liquid, if you have something else inside the boundary also, the force distribution is the same. Means the resultant of those red vectors will still be the same. Therefore, in this case also, the buoyant force will be density of liquid into volume displaced into g. That is nothing but the weight of the liquid displaced. So irrespective of what is present in that boundary, the buoyant force depends on the volume enclosed in that boundary and the liquid outside it. Density of liquid into volume inside that boundary multiplied with g, that is the buoyant force. But again, remember the condition, this is for a non-accelerated fluid, non-accelerated liquid. Fine. So in any case, now see, we took the case of non-accelerated liquid, we wrote equilibrium condition and we got this buoyant force. Even if it is a non-accelerated fluid, what am I saying? Even if it is an accelerated fluid, the analysis will be done this way itself. If you want to know how much buoyant force acts on an object, replace the object with the liquid itself. If everything is liquid itself, it will be in equilibrium relative to the container. Objects, some other material may sink in a liquid or float in a liquid, but the same liquid will not sink in the liquid or float in it. Why will that happen? Why will some molecule suddenly decide to go down? They won't. Okay, they'll stay where they are. So in any case, if you want to calculate buoyant force, or if you want an expression for buoyant force, replace the immersed volume with the liquid itself, surrounding liquid itself. How much ever force is needed to keep that liquid in equilibrium, that much is the buoyant force. Okay. Right. Now we took the case where object is completely immersed in the liquid, which need not always happen. Object can be partially immersed also. We'll still consider, I mean, in this class, we'll only consider non-accelerated fluids. Next class, we'll see accelerated fluids. So I won't be mentioning it. Assume the fluid is non-accelerated. Let's say an object of some random shape like this is floating on this liquid. It is found to be floating. Okay. Now, one of you tell me, or all of you tell me, what are the forces acting on it? What forces act on this object?
Sir, weight and buoyant force.
Okay. Weight is one force and force due to pressure distribution. That is buoyant force. Correct. Okay. Now for buoyant force, you don't separately have to say force due to atmospheric pressure, force due to liquid pressure. Okay. All force due to surrounding pressure is called buoyant force. Together called buoyant force. So weight and buoyant force are the forces acting on it, and assume you find it to be floating like this. It's quite common for some objects to float on liquids. Okay. Let's say this object is floating in such a way that a volume Vi is immersed. Total volume is V. Total volume of the object is V. Immersed volume is Vi. Okay. Density of the object is rho naught. Density of the liquid is rho L. Fine. Write the equilibrium equation. You know what forces are acting on it, no? Just balance them. That's the equilibrium equation. And based on that, derive the ratio Vi by V. How do they call this in questions? Vi is immersed volume, V is total volume, no? So this is called as fractional volume immersed. Means what fraction of the volume is immersed in the liquid. Do this, all of you. I'll give you 2 minutes. Pawan, can you tell the equilibrium equation? Like there are two forces acting on it, weight and buoyant force. You'll have to equate them. How do you write expressions for them? Can you unmute and respond? Is it possible? Okay, fine. The weight of the object depends on its density and its volume. So weight of the object is density of object into total volume into G. mg, mass of object multiplied with gravity. Buoyant force, on the other hand, we just proved that buoyant force is always density of liquid, not always, sorry, in a non-accelerated container or fluid. Buoyant force is weight of the liquid displaced. Now, imagine how much liquid this object is displacing. It is only displacing this much liquid. Immersed volume. Okay. What I mean is, had that space been filled with the liquid itself, the forces from the surrounding liquid would have kept it in equilibrium. Okay, that is what is buoyant force, or that is how much is the buoyant force. So how do you calculate that? That liquid's weight is balanced by these forces, no? Some other object may sink or float, some other material may sink or float, but if that space is filled with the liquid itself, it will be in equilibrium. Okay, therefore buoyant force is just balancing the weight of the liquid displaced in this case. That's all. So buoyant force is density of liquid into volume immersed. Only that much volume matters, multiplied with G. That's all. G cancels. So immersed volume by total volume is density of object by density of liquid. That is the fraction of volume that will be immersed. Okay. For example, suppose object density is 0.5 gram per cc, liquid density is 1 gram per cc. Then the ratio will be 0.5 divided by 1, means 1:2. Means half exactly will be immersed, half will be outside. Okay. Have any of you seen photos of icebergs? You know ice floats on water. Okay. Have you seen photos of icebergs? Iceberg, Titanic struck the iceberg and like lost balance and collapsed, no? Anyway, these kind of images are quite common. Okay. So when ice floats on water, this is what actually happens. We discussed in the last class also, an object cannot float staying completely outside the liquid. It has to be immersed. Some part of it has to be immersed. Okay. When ice actually floats on water, this is what happens. In case of ice and water, 90% of ice is below water. Only 10% you see outside. Okay. You may have seen motivational quotes also based on this. This is effort or background effort, and this is what you see outside. Okay. Success or whatever. Okay. Never mind. Now, what this shows, or you can explain this in terms of densities. Water has a different density compared to ice. Fine. Now, 90% is inside, 10% is outside, means the fraction of volume immersed is 9 out of 10 parts. And we just derived that the formula is density of object by density of liquid. Object here is made of ice. Liquid here is water. That means density of ice by density of water is 9 by 10, 0.9. So ice density is 0.9 times water density. Okay. So if you know the densities, you can tell the fraction of volume immersed. If you know the fraction of volume immersed, you can tell the density. Any one way you can be asked questions. Fine. Next case. Suppose there is some random object which is fully immersed in a liquid and released. We are not holding it now. So when some other material is placed in a liquid and released, it's possible that it sinks, it's possible that it rises also. It depends on the forces acting on it. Now you know what forces acting on it. Weight act on it, weight and buoyant force. So let's say density of liquid is rho L and the density of object, okay, density of liquid is rho. Fine, 3 rho. Object density is rho. Fine. So the material of the object is less dense than the material of the liquid, Okay. You know weight and buoyant force will be acting on it. Okay. Non-accelerated liquid, as I said. Assume volume is V. Write these expressions, that's all. How much is the weight? How much is the buoyant force? How much is the net force on the object? And based on net force, how much is the acceleration of the object? Solve this quickly. Aishwarya, can you tell the expression for weight of the object?
Sir, rho V into G.
Rho Vg. And weight acts in the vertically downward direction. Fine. Aishwarya, continue. What is the expression for buoyant force on the object?
Sir, 3 rho Vg.
Okay. Density of liquid into volume displaced into G. So 3 rho volume displaced is complete volume into G. So definitely buoyant force will be dominating here. And if buoyant force dominates, the object is going to rise up. So how much is the net force? Stronger force minus the weaker force. Net force will be 2 rho Vg. And acceleration from Newton's second law is net force divided by mass of the object. Mass of the object is rho V. So the acceleration will be 2g in the upward direction. Okay. See, generally, when an object is immersed in a liquid, weight of the object will be rho naught into V into G. Let's assume complete immersion. And buoyant force will be rho L into V into G. Now Vg is same, that's fine. If rho L is more than rho naught, density of liquid is more than density of object, buoyant force will be greater than weight. Means the object will have a tendency to float. it will start rising up if you release it. If density of liquid is less than the density of object, then weight will dominate, the object will sink. So if object is denser than liquid, it will sink. If liquid is denser than object, it will float. If both are of same density, it will stay wherever you leave it. Weight and buoyant force will balance, net force becomes zero. Wherever you release it, it will stay there. Okay. And let's discuss one more point also. How did we prove that buoyant force is equal to how did we prove that buoyant force is equal to weight of the liquid displaced? Had that space been occupied by the liquid, that liquid would have been in equilibrium under the influence of buoyant force. That is the logic. Remember the logic, all of you. That's very important. Whatever is immersed in the liquid, imagine that space being filled by the same liquid surrounding it. If it's the same liquid, it will be in equilibrium. Based on that, we are calculating buoyant force. And equilibrium means translational as well as rotational. Now, based on translational equilibrium, we say buoyant force is equal to weight of the liquid displaced. Upward force is equal to downward force. So that gives us the magnitude of buoyant force. It gives us the direction of buoyant force also. But see, had this space been filled with the liquid, okay, consider the right side diagram. Had the space been filled with the liquid itself, that part of the liquid will also be in rotational equilibrium. No? Now there are two forces acting on it, weight and buoyant force. And that part of the liquid is in rotational equilibrium. Rotational equilibrium means what? Net torque is zero. How can net torque be zero here? Both forces should have the same line of action. Then only net torque can be zero. Magnitudes are same. Weight to buoyant force, they have the same magnitude. They are in opposite directions. Now you take an axis wherever you want. About that axis, whatever torque one force is creating, the same torque the other one should create. Only then that part of the liquid can be in equilibrium. And how is that possible? Their lines of action must be same. Directions are opposite, line is the same. Okay. What does that mean? That means buoyant force should also act through the center of gravity of what? Of the liquid that has been displaced. Because had there been liquid, liquid would have been in equilibrium. Means buoyant force acts at the same point or acts along the same line along which the weight of the liquid acts. Okay. And we show weight to be acting at the center of gravity, okay, which for small sizes is the center of mass itself. Therefore, buoyant force also should be shown acting through the center of mass or center of gravity of the liquid that has been displaced. That point is called center of buoyancy. So where should you show buoyant force to be acting? Buoyant force must be shown acting through center of gravity of displaced liquid. And this point, okay, center of gravity of displaced liquid is what we call center of buoyancy. Okay. So in this case, you can notice there's an object and there is a different liquid surrounding it. I see object's weight should be indicated through its center of mass. Buoyant force should be indicated through center of mass of the displaced liquid. Now we assumed the object to be I assumed the object to be uniform here. If object is uniform, then okay, we can get some rough idea of its center of mass. If you replace the object with liquid, that liquid also will be uniform only, no? It's the same liquid everywhere, so liquid also uniform. Uniform object, uniform liquid, both their centers of mass will be the same anyway. That's why I directly showed buoyant force also to be acting at the same point where the weight is acting. Okay, but see, it's possible that the object is non-uniform. Okay, for example, consider a sphere. These are slightly in-depth discussions. You may not find these in all books, but these are important. Okay, for advanced level, these are important. Consider a sphere which is made like this, half made from one material, the other half made from a different material. Okay, let's say left side is lighter, right side is heavier, denser. So you can take densities like this. maybe rho here, 2 rho here. Now, where will the weight of this sphere act? You can treat it as two hemispheres. Do any of you remember where the center of mass of a solid hemisphere lies? Solid hemisphere. It lies at a height of 3r by 8 from the base. Okay. Here. This height from the center of the base will be 3r by 8. Okay. So the part which has density rho, its center of mass is here. The part which has density 2 rho, its center of mass is here. Both 3r by 8, 3r by 8 only. But the part which has density 2 rho has more mass. Okay. And you know center of mass will favor the heavier mass. Therefore, the effective center of mass of the sphere will be somewhere here. It won't be at the geometrical center of the sphere. So the weight of this object will be acting like this. Okay, I should not use white. Let me use red. This is the effective center of mass of the sphere. Its weight will be acting like this. Now, what about buoyant force? Buoyant force depends on pressure distribution. And buoyant force can be visualized if you imagine that space to be filled by the liquid itself. Okay, I will do that on the right side. Imagine that space being filled by the liquid itself. Liquid is uniform. Then where will the center of mass of the liquid be? At the geometrical center. Therefore, buoyant force acts through this point, the geometrical center of the sphere, like this. Now, which force is greater depends on overall density and all. We'll discuss such cases also. Object made of two different materials or multiple different materials, whether it will sink or float, we'll discuss. But see, buoyant force has one line of action. The weight of the object has a different line of action. Then their torques won't cancel. Effectively, what will happen? This object will rotate. And finally, how will it settle in a real life situation? The heavier part settles on the lower side. So finally, what you will see is the sphere settling like this. Heavier part goes down, you know that. This will be the situation. Once it settles like this, then both centers will be on the same line again. The sphere's center of mass is somewhere here. The displaced liquid center of mass is here. Now the buoyant force will be acting like this. Weight of the object will be acting like this. They are along the same line. Then the net torque becomes zero. It settles in that position. Okay, it may oscillate for some time and finally it settles in that position. The denser part will go down. Okay, so remember that there is something called center of buoyancy also. You can't blindly indicate buoyant force through the center of the displaced volume. Wait. Buoyant force can be indicated through the center of the displaced volume. Weight of the object cannot be indicated. It depends on the mass distribution in that object. Fine. And here also they can twist the question in many ways. This also is not necessary. What is not necessary? That it always acts exactly through the center is not necessary. Suppose by some means they keep one liquid on one side, another liquid on the other side. Then the force pushing from this side will be different. Force pushing from that side will be different. Then that may not be the center of buoyancy. They can change the situation. Okay, anyway, we'll solve problems, you'll understand. So what have we discussed so far? Why buoyant force is equal to weight of liquid displaced in a non-accelerated case. Okay, that we have discussed. Then fractional volume immersed. Okay. Let us next discuss flotation. Now we just discussed one point before center of buoyancy, that if density of object is greater than density of liquid, it sinks because weight will dominate buoyant force. If density of liquid is greater than density of object, then it rises or floats. Okay. Now we know ships float on water. What are ships made of? What material are they made of? What material are ships made of? Guess at least.
Iron or steel?
Metal. Okay. I fine. Exactly, we don't know. They could be alloys most probably. I don't think iron will be used because iron will rust. No. So it'll be a bad choice actually. Anyway, the body, the main outer body of the ship is made of metal. Metals are usually denser than water. Then how is it that a ship made of metal, which is a material denser than water, does not sink in water? Why do ships float? Any guess? Consider a sphere immersed in liquid. Assume it's a solid sphere, completely filled with the material. Now, there will be two forces acting on it, weight and buoyant force. Assume density of the metal, okay, is greater than density of liquid. Fine. Therefore, its weight, okay, because density of metal is more than density of liquid, definitely weight will dominate the buoyant force. How do you write expression for weight? Density of metal into volume into g. That is the weight. How do you write expression for buoyant force? Density of liquid into volume into g. Okay. But observe carefully, weight depends on volume occupied by the metal. Okay. So the V that you see in weight is volume occupied by metal. Whereas the V that you see in buoyant force is volume of liquid displaced. Fine. In this case, both are same because the sphere is completely filled with material. The volume occupied by metal is same as volume of the liquid displaced. Therefore, weight will dominate buoyant force. But what if you start creating empty spaces inside that sphere, cavities, or space filled with air? Air density is negligible compared to metals and water. Okay. Do any of you know how much is the density of air? How much is the density of air? In chemistry, you must have studied. No. Can you tell me an idea to calculate density of air at least? Density is mass by volume. How to calculate density of air? You should know how much mass occupies how much volume. What do you know about ideal gas at STP? How much or how much gas occupies how much volume at STP? Anyone? How much gas occupies how much volume at STP? A
Say
mole
one
concept you
mole
must have studied, no?
gas that
1 mole
say 1 mole
occupies
of gas occupies 22.4.
0.4 liters. Okay, correct. From that, you can get a rough idea of density of air. 1 mole occupies 22.4 liters. Okay. Now, 1 mole of air. Air is a mixture. It's not a single gas. You know it is how much? 79% or 80% nitrogen you take, 20% oxygen you take. Other gases are in trace amounts, you can ignore. Okay. So 80 by 100 moles of nitrogen plus 20 out of 100 moles of oxygen. Get the mass. You know their molecular masses, no? Nitrogen, oxygen. You can get the mass of 1 mole of air and you can get its, you know, its volume. Divide them, you'll get density. It'll be 1 point something, very small. Density of water is 1000 kg per meter cube. Density of air is just 1 point something kg per meter cube. Negligible. Okay. Fine. Let's come back to the point that we were discussing. How do ships float? Ships are made of metal, but how are they managing to float is the question. So you consider a ball completely made of metal. Definitely its weight will be stronger than the buoyant force. It will sink if you release it in water. But in this ball itself, if you create a cavity, what do you mean creating by creating cavity? Keeping some space empty. If you do that, effectively what are you doing? You are decreasing the volume occupied by the metal. If you decrease volume occupied by the metal, the weight reduces. What about buoyant force? Will it reduce? Or is the volume of liquid displaced still the same, therefore the buoyant force still the same? What do you all think? Buoyant force will remain the same. So liquid is displaced by metal, liquid is displaced by air also. Okay. So the volume of liquid displaced is still the same. That complete sphere volume liquid is displaced. But the complete sphere volume is not filled by metal. Only some part is filled by metal. So the weight reduces. So you can imagine the weight vector becoming shorter. Okay. You increase the size of the cavity, the weight vector becomes even shorter. Okay, the way I am drawing it, there will be an imbalance. That's fine. Just to make you understand how flotation occurs. Fine. You create sufficient amount of cavity, the weight can exactly be balanced by buoyant force. And if you create more cavity than that, okay, if you create more empty space than required, the weight will become so less that the buoyant force will start dominating. And if buoyant force is dominating, the object will stay partially outside. The object will float. That is how flotation occurs. Okay. Now, you may say, sir, boat is not a sphere. Boat does not have a cavity. Boat has a cavity. How? Think of it like this. Just a moment. Like from the side, if you see, boats look like this, but boat is an open vessel, right? It is open at the top. So let's consider it like this only. Okay, I think it will be better if I use thicker ink. Okay, let's say this is the metal with which the boat is made. You are looking at it from the side. When you immerse this in a liquid, okay, water mostly, imagine trying to immerse this boat in water. What will happen? When it is completely outside, weight will be the only force acting on it, so it will have to go down. As it goes down, not only the metal, the air inside it also, the air inside the boat also will displace water. Situation will be like this. Fine. So look at what is happening here. This is the actual volume filled by the metal. Okay. And this is the volume of liquid displaced. They are different. The actual space taken up by the metal is different. The actual volume of water displaced is different. Okay. So the boat will go down to a certain extent. It won't sink completely. Of course, it depends on how much weight you put on it. But as the boat goes down into water, it's not just the metal displacing water. The air inside the boat, the empty space inside the boat is also contributing to the volume of displaced water. Okay, or volume of displaced liquid. As a result, once the boat sinks to a sufficient extent, not completely, but to a sufficient extent, maybe this much. Okay, just a random example that I'm taking. Exact value depends on exact materials and all. So there is cavity here. Fine. The boat takes air along with it into water. Fine. So what will happen? The volume occupied by metal is fixed, but as the boat goes deeper and deeper, okay, or as the boat enters into water, the volume displaced goes on increasing. And at one particular level, the weight of the liquid displaced will be equal to weight of the metal. Means the buoyant force will be equal to weight of the boat. It will settle at that level. Okay. If you add some extra weight, okay, you put some cargo on it, then that will press the boat further down. If you keep on adding weight, at some point it will sink completely. Okay. So that is possible. But if the weight is kept under control, this is how flotation occurs. This is how a boat or a ship floats. Okay. So next class will be solving problems like this. Like how much volume should be kept empty such that the object metal manages to float. Okay. Or how much volume should be filled with a lighter material such that on the whole the ball manages to float. Such questions we'll solve in the next class. Next class we'll discuss buoyant force thoroughly and complete it. Okay. And when will I take the next class? Tomorrow itself. Because Wednesday, Thursday, I may not be able to take classes. So tomorrow evening, probably at 7:30, I will start the class. Okay. Thank you all. We'll continue tomorrow.